Hello and welcome to another tutorial. So this time we are going to be taking a look at something called design patterns. So design patterns are standard or common ways of solving a particular problem. And design patterns exist across pretty much every programming language, and similar patterns you'll see that replicated in slightly different ways tailored to each language across all of those. So we're going to have a look at a couple of common ones, and these are ones that I use a lot. So there are a lot of design patterns out there. There's only really a subset of ones that you tend to use frequently, so I'm going to focus on those. So design patterns are all about solving a problem. And the first one we're going to look at is one of the most common ones that we use it a lot in my own projects, something called a singleton. So the idea behind a singleton is that it is something that only one of it exists. And because only one of it exists, it makes it very easy. We can optimize how we actually find and access it. So it gives us something that we can very quickly access. So this is a really handy thing for stuff like manager classes, stuff like that. A singleton can often be an appropriate structure there for it. So what I'm going to do is I'm going to create just an empty game object that'll be our game manager. And I'm going to create just a cube that I'll put somewhere in the world. I'll call demo cube 1. So I'll then set up my scripts here. So I'm going to set up two scripts. One is going to be the game manager script that will turn into a singleton. So we'll set up a script that we call game manager. And then I'll also set up a script that's for that demo cube. So I'll have a script here that we'll call demo cube. And once Unity's processed those, we'll just attach them to the different things. So we attach scripts to each one. So then now I'm going to go and take a look at these scripts. So what I want to do is I want it that our demo cube, that there is something on it that the game manager controls. So I'm going to set that up initially as a particular thing. So let's have a serialized field float rotation rate. And we might set that to, let's say 15 initially. And then this is something where I could set up some parameters for accessing it. So I could set up a public float rotation rate that we map to that. Then in our cube, so if I go to the demo cube, what I could do is, the way that I'd have to do it in this is I'd have to go, okay, well, if I know there's one of it, so I could either manually link it, which only works really if the cube is there from the very beginning, or I dynamically link it. So I need to find it. So that would mean with the cube, I have to do something like a find object of type, game manager, and then usually, because that might be a parameter that changes, I end up needing to have a cached version of that. So I'd have, a cached game manager that we would link up like this. And then in the update here, I could go, well, transform, and we could tell it to rotate. We will use the version where we just give it the individual values. So I could go, okay, well, cached game manager, rotation rate by time, delta time. So we could absolutely do this. This is one of the ways that we could set it up, and this is sort of the approach that we might be familiar with. So we haven't made a use of a singleton yet. We just want to make sure that it actually works. Always be wanting to be testing frequently. It's cool. So it works. Should do. We were expecting that. But yes, we're having to do a find. Finds aren't fast. They actually are quite an expensive operation. So if you had a lot of things needing to do this, this gets quite slow. And there might be legitimate reasons why we're having to go and talk to this game manager right when we start up or regularly. And so that's really a slow process if we're doing that a lot of times. And so the idea behind a singleton is if we use that singleton pattern with the game manager, we can simplify this. And we can also improve the performance of it a lot. So how we generally structure a singleton is you'd have something where we have a public static. So by marking a variable as static, the variable belongs to the class, not to the instance of the class. It's a really critical difference there. So we want a static function here, instance, and we can go with the get and private set. Then in awake, and it's quite important we do this in awake. What we want to do is the simple version is we would do instance is equal to this. So we have that public static variable, we've now linked up the instance, but the idea behind a singleton is it should enforce that there is only one of it. So we want to check if instance is somehow not equal to null. We want to know. So first thing we want to do is we want to display an error for that, because that's actually quite serious. That breaks an underlying assumption and an underlying rule. So if you have those sort of core assumptions, core rules in your project, really important, make sure you advertise a very loud error if those assumptions are found to be broken. So, okay, we've got an error that we'll log out here. So we'll say found duplicate game manager on, and we log out the game object name so we can easily find it, destroying this version. So what we actually do is we do a destroy of that game object. Again, we could just destroy the script, but we want to actually make sure that this is handled very loudly and that it doesn't escape notice. So we destroy the game object. So does the instance already exist? So what we're enforcing here is that the oldest version of this singleton is the one that actually persists. So this block here is all that we need to essentially turn any class into a singleton. But again, that implicit, well actually more explicit assumption there that we enforce is that there is only one of them. How this changes the code is, well, we don't need to cache the game manager anymore. Don't need to do a find anymore. What we could do is we could do game manager dot instance. And that will allow us to directly access the rotation rate. So this results in smaller amount of code. It's a lot cheaper than if we're doing finds, things like that. And we'll run it and we'll see that it still works. So cube still rotates around as we would expect. Now, there are further things that we could do with this, because having to write instance every time can get a little bit messy. So we could do something where actually this rotation rate, well, I could make that static. And then what that refers to is that refers to instance rotation rate. Then our logic here just becomes game manager dot rotation rate. So again, cleans up the code, simplifies it. We can do a similar thing with functions. So we could have a function that might be a public static void, and this might, be something where, let's say it's called perform rotation, and we give it a transform. Now we've made this one static, but what we could then do is we could then have, and this could be private. You generally don't inherit from a singleton. That's the other thing with it. Singletons are usually not something you inherit from. So we'd have private void perform rotation, transform target, and you'll notice it already has one with the same parameter type, so we have to actually make sure these have slightly different names. So what I usually use is I'd call that something like perform rotation internal, and then again we can do this. So it allows us to have public interfaces, but there are private implementations. So that is actually sort of another thing you'll see as a design pattern, something called private implementation. This is a very thin version of that, where we have public interfaces, but the actual implementation logic here is private. So then this could do target, rotate. Actually, we might make this set random rotation. Oh, cool, we'll go for that. Actually make it a little bit different in terms of what it does. So set random rotation internal. So this can go, well, target Euler angles. There's a new vector 3. And we just, for each one, we'll do a random range, 0 to 360. We'll just do that for each one of them. And that gives us a function that what we could do for the demo cube. Well, game manager, set random rotation, transform. So again, really clean interface for it. And it means we do have to write a little bit more sort of boilerplate here, but it gives us the advantage that we have this really clean setup of how it actually talks to it. And it's very efficient. So again, puts a random rotation on it, and then it's rotating that cube. So very effective pattern. Now, there are a couple of things to watch for with singletons. So one of the things is that in terms of when you're talking to the singleton, if you are running code that is happening at the destruction stage of an object, that's something where you actually do often need to null check the singleton. So if I had something in here where, okay, void on destroy, and this was going to be doing some talking to the game manager, I would actually want to do a check first of if game manager instance is not equal to null. Because if we are in the process of destruction, we don't have necessarily control over the order that the objects are being destroyed in, which can mean that that singleton object, because it's something attached into an object in the world, it could have been destroyed before the destroy code runs for something else. So if you're doing logic that's happening in the destruction stage for a mono behavior, a game object, you may need to do a null check there before you access a singleton, just as a safety measure. Similarly, I would not do any logic in a wake that tries to talk to a singleton. That's generally in Unity a no-no, regardless of whether we're working with singletons or not. In a wake, you only work with the class that the code is running in. You don't talk to other components or other game objects. So if you're working with the singleton, you wait until start is run, and then you can talk to the singleton. So that's just a couple of things to watch for. Don't talk to singletons in a wake. In general, don't talk to other objects in a wake. And on destroy, you can attempt to talk to the singleton, but you should do a null check first to ensure that it actually exists. Because if it doesn't, then you want to make sure it's not trying to run the code, because otherwise you'll get null reference exceptions. So it's okay to do a bit of a safety check like this if you need to. I'll just add in specific comments for those, just so that we have a reminder there for that. So don't try to talk to the singleton in awake, or generally other objects. That's also generally something we want to avoid. So if we're being destroyed, null check before talking to the singleton. because when our scene gets unloaded, everything gets destroyed, but we're not necessarily controlling that order. So the game manager, in this case, or any of our other singletons, could get destroyed first. So, okay, that's pretty good so far. We've added in a couple of useful parameters here. We've added in seen different ways of being able to make these safety checks here. The other thing that we should add in, because we did identify that with a singleton, we generally don't want to inherit from them. So we can actually prohibit inheritance by marking this as sealed. Because what will happen if we mark that as sealed, and then say down here, won't work, and we try to inherit from game manager, we will notice you can't derive from a sealed type. So when you're working with your singletons and you need to ensure that inability to be able to inherit from them, do make sure you mark them as sealed. So in terms of areas where you might want to use singletons, so manager classes are often a good scenario for that. If you're working on a single player game, sometimes that player actually can be a really useful thing to be a singleton. If you have stuff like a central UI script that's controlling a lot of stuff, your UI could be a singleton. So there's a lot of different things there that you could make a singleton. It can be really, really handy. I use that also for things like my settings manager. That's actually a singleton, and that persists. That's in a don't destroy unload, so it's always around. So there's a lot of really useful things that you can do with singletons like that. Okay, so that's the singleton pattern. And it's one of the main ones we use in Unity. Now there are other design patterns as well that want to have a bit of a look at, and some of these will be, close to the sort of, I guess, more formal version of the design pattern. Other ones are going to be a little bit variations on it. So one of the ones that does at times come up, in particular if you've got a lot of stuff dynamically spawning in a game, something called a factory pattern. So a factory makes objects, and usually part of the thing with the factory pattern is it's not just making an object, it's configuring it. So a factory might only make sort of a particular type of object. It can make multiple ones, but it handles a bit of configuration of it. So what that means is your spawning code can be quite simple, and a lot of the logic gets handled by that factory. So to do this, the equivalent of sort of those things that we would be manufacturing in this would be prefabs. So what I'm going to do is I'm going to set up a folder for our prefabs, and I'm going to set up that prefab. So what I'm going to do is I'm going to create a cube, and I'm going to give this a script, and this is going to be a manufactured cube, and I'll attach this onto that. And then we'll make that a prefab. So this will be the template cube. So that can go there. We'll get rid of that one in the scene. And then what I'm going to do is create our cube factory. And we'll give it a script. So it has a script here, cube factory. So again, you can have cubes that factories that might produce multiple types of cubes. So in particular, say you've got a game that has a lot of different types of AIs that can spawn. They'll often have a common sort of hierarchy. There'll be an inheritance set up there. So you could have something that is essentially an enemy character factory, and that might be spawning all different types of ones. And what it does is it gives you back a pre-configured one, which can be really handy. So, okay, let's go to our cube factory. So it's going to need the template object. So it's going to need the cube prefab. Now, in this case, we've got a single prefab that we might configure in different ways. Now, a factory, you could have multiple different prefabs and it could randomly pick. you could have multiple different prefabs and you tell it the type of one to pick, or the one from a particular set. So although I'm just using a single template object here, that is absolutely not what you're required to stick to. You could be using multiple different ones there with this. So okay, we've got that prefab. With our factory, it's often useful for the factory to be a singleton so that we can just directly talk to it. So because I've got my singleton code all in one block intentionally, I can bring that over here and we'll see very little changes. That becomes cube factory, that becomes cube factory, and we're done. We now have this is a singleton. Okay, so we've made this a factory and we'll have a function and we'll follow a similar pattern to what we did with the other one. So this, I want it to give me back a manufactured cube, and this is going to have, well, it'll be build cube. We'll follow exact same as what we did with the other style, where that will be build cube internal, and we return that. And then we have our private manufactured cube, build cube internal, and we're going to remember and mark this as sealed as well. So what this needs to do is it will create the game object. So new, we'll call this cube game object. We can instantiate, and we can give it our cube prefab. And then what we would return is cube game object, and we get the component. But we might want to be doing some extra logic on that first. So we could have manufactured cube script, like that. And then we return this. Now we haven't done anything in terms of controlling the placing of this. So that could be something where we might want to give it a particular location. So when you're asking the factory for something, you sometimes give extra information there. So you could say, okay, well, I want a cube at a particular location. So you could give it a location, and we could give it a range, and we'll pass these through. We're going to have location, range. Now in terms of where this cube gets placed then, well, we need the version of instantiate where we give it a position and we give it the parent. So we'll have spawn location, give it the identity, and we need to give it a root transform that it's linked to. So parent transform. So firstly, let's generate that location. Well, the location, that is going to be location plus a new vector 3, and we do a random range, and we could do this a random range from minus range to range, and we do that for each of the particular ones. So it essentially spawn in a sphere around this. We've got the location. We need a transform. Parent transform, and we'll feed this through as well. Parent transform. So that's good. We've instantiated it, so we've picked a random location, we've instantiated it. I've grabbed that script because there might be bits of configuration we want to do on that. The key thing is we've got a fairly simple setup for this. So the game manager could have something where it's doing the actual spawning. So this might be where what I'm going to do is f input get key and we'll go for a get key down, key code S. Then I want that to talk to our factory. So I want it to go, hey, cube factory, build a cube. I want this to be a parent of this particular object. The location, I want to use my position, and let's go for somewhere within a 10-meter range. So that means the process of doing the instantiation, placement, things like of that is handled for us. We can link up our prefab. So we go to our assets and link up the template cube. So what this will mean is now every time I press S, it should spawn a new cube. And so they all add in around there. So the factory's taking care of that. What it means is if there's further things we want to do, it's in a very contained spot. So our logic that needs to work out a spawn location doesn't get bogged down with a lot of infrastructure stuff that might need to happen just every time we spawn things. Also means that we've got a lot of similar things being spawned. It's all kept in the one spot. So using factories can be a good way of sort of partitioning up the code like that and making it a bit cleaner, a bit easier to manage. And for example, in a case like this, well, we want these to have a proper name. So what I could do is I could be tracking here int next cube number, might be 1. And then what I do is after I've instantiated it, I set its name to manufactured cube, and we add in the next cube number, which I then increment that. So now we're enforcing everything has its own unique name. If there was different things I needed to configure on that cube script, I could easily go and do that here because I've retrieved it. So now if I go and run this, we'll see all of the ones that get spawned will have a unique name. And that can be really handy. It's one of the things, if you're doing dynamic spawning of stuff, I really recommend making sure you're controlling the names. It makes it so much easier to actually find stuff and to track down issues if you've got unique names there for things. So that's sort of the general with the factory pattern. As I said, it's not something that, it doesn't make our code more efficient. It doesn't really make it less efficient, maybe in the most trivial of ways. So it doesn't take up extra time. It is a bit more code. So there's always the question then of, well, why would I bother? If it's something that doesn't make it faster, it doesn't make it that I'm writing sort of a lot of less code. There's potentially some code saving, but why bother with it? And it is something where if you're doing a lot of spawning in a lot of locations, it can give you a saving, especially if it's spawning similar things. You can reuse the logic. But it's also about partitioning the code and keeping the code as small as possible. It's something where you want to try and solve something with as little code as possible and have your functions be as short as possible, because that makes it a lot cleaner, a lot easier for debugging if you're able to see pretty much a function entirely on the screen. So having a factory allows us to, in some cases, reuse code, which is great. It allows us to keep related code in the same area for doing the spawning, and it allows us to simplify other code. So the advantages for it are more so on the side of being able to make the code easier to maintain and work with, and lessening the risk of bugs and things like that could be occurring and creeping in. So it's really about that reliability and robustness for our code. So the final thing I want to show you is something that it's sort of an extension or modification of something called the Object Observer pattern. So the Object Observer pattern is something where you can have, multiple objects. So they could be, AIs in your world, and you can have an observer of them. and that observer can be listening and reacting to particular things that are happening. You can have stuff that also is, listening to multiple sources, or multiple sources listening to the one thing. You don't tend to see that sort of pattern very explicitly implemented in Unity, and the reason for that is because there's the very robust event system stuff in both C# and also Unity specific stuff. So that event-based approach of having multiple listeners, being able to push data to them, that actually is a lot of the stuff we get from Object Observer. So it's not something we tend to see used explicitly within Unity. But there is a scenario that we do often run into where we might need to maintain a registry of things. So in that scenario where, say, we have characters or things dynamically spawning in, we might need to have some central thing that is able to talk to them. Because characters might need to be able to find out, well, who are all of the other characters around, so that they can interact with them. So that's something where you could have every character do a find object of type and every character handle managing its own list. But that has a lot of overhead. We're constantly doing find objects of type then potentially. There's a lot of sort of fragility to a system like of that, where not one thing is maintaining it, but multiple are maintaining it. So what we can do is we can set up a registry. So I'm going to do that, and I'm going to put this as a separate class. And what I'll do is I'm going to create a cube registry. And I'll show you how we actually set this up. So we're going to create an empty object here that will be a cube registry. And we'll link this up. So the idea with this is all of those dynamically spawned cubes will be registered with this. So our cube registry, in something that I'm sure is going to not be a surprise, we're going to make it a singleton. As I said, we keep coming back to this use of singletons, and that's because they solve that problem of discovery very efficiently, very well. Like, there's a reason they're used quite a lot. They're a very effective design pattern. And when it's a very small chunk of code, it's pretty handy. Again, we're going to mark that as sealed. So, okay, what we want to be able to do is we want to have registration and deregistration functions. So we'll follow same approach we have with the other singletons. And we'll have a public static void register, and it gives a manufactured cube. And then we'll have a public static void deregister. Again, provides the cube. And we then have the internal versions of these. So these ones cease to be static, and they become internal. And we make them private, like that. So these will run instance register internal with the cube, and this will then run instance deregister with the cube. Now, what we then do in our manufactured cube is it's pretty straightforward. In start, you can go cube registry, register this, and then on destroy, we do cube registry, deregister of this. Now remember, that destruction logic, if there's cubes around and we're unloading the level, this could cause a null reference exception. And whether it does or not is going to depend on where things are in the level. It's going to depend on things that are outside of our control. But that's okay, because we can work around that. As I said, we do this null check. So what I would do is I could check here if instance is not equal to null. Now you'll notice I'm only doing this for the deregister. I would not ever do that for register, because at the point in the life cycle where register is running, it is a reasonable expectation, a reasonable assumption that the instance exists. Deregister, could validly run at a point where it doesn't exist. So it's something where you want to, null checks and safely handling things like of this is something that is valuable to do, but whether you do that or not is something you should be making sure you're thinking about. Okay, is this something where I'm adding in a safety check for a very reasonable, safe scenario that could happen, like the deregister, or is it a high-risk scenario where if that happens, something really bad has gone wrong? And register failing, something really bad has happened if register fails. So that actually is something I want it to fail noisily. I want it to trigger an exception. So register and deregister, we need to keep track of these cubes now. So the data structure we use for this matters, and which we choose depends upon how we are working with it. So because different containers, so like lists and dictionaries and hash maps and things like that, have different performance characteristics. They generally optimize particular operations at the expense of others. So something like a list, we can access random elements in it really fast. We can loop through every element in it really fast. But insertion and deletion or searching are slower. Something like a map structure, things like that, we can find stuff really quickly. We can insert and remove things very quickly. But iterating over everything is usually more expensive. So depending upon the structure, it needs to be linked to the operations we're going to perform. So in our case, I want to only support really looping through these. So that's something where I would use a list. But bearing in mind, that means that adding something into that list will come at a higher cost. So what I would be able to have is a public list manufactured cubes. And this would be our registered cubes. We won't actually have that as public. So that's registered cubes. It's like that. And again, I will do a setup where I want to make it that's easily accessible via a static interface. So we'll have a list of that links to instance.registered cubes. Now that again is something that we might potentially need to do a null check on. It would depend upon whether we are ever working with this in the destruction side of things. Generally shouldn't be. So that's something where it's a case of like, if I don't have a good use case for it now, I'll let it be at a point where it could trigger a null error. And so when that null error happens, then I can assess that situation and see whether I need to change the variable or whether I need to change how I'm interacting with it. So I tailor it to the particular scenario. Okay, so we've got our list of ones. So what we would do is registered cubes, add. Now, that cube could already be there. So we should, as a safety check, potentially, have a look and see, well, if registered cubes contains that cube, then, well, we don't need to add it, so we can return. But that's also a scenario that I'm not expecting to have happen. So I want to actually cause an error for that. So attempting to add cube name multiple times to the registry. So again, always make sure you're logging out errors for situations that should not occur. Deregister, so it can go a remove. And so with that, you'll notice remove returns a Boolean. And likely that Boolean is going to indicate whether it did actually remove it or not. So we could check if it failed to remove it, then again, debug log error, attempting to remove unknown cube from the registry. That way, if we do try and remove something that wasn't there, we get an error message for it. So let's test this out. So manufactured cube, all of these things should work. It should just be registering and deregistering the things happily. What I can do as a way to, just for debug purposes, see that that is working, so I'm going to make that public for now. That'll just let me see the registry appearing here. So we'll run it and we'll spawn these cubes. So that's looking good. Now we want to make it that those cubes, let's make them destroy after a time period. So what we could do is, and this is where I might go back to the factory, and we'll go cube script set life in a random range from 0.1 seconds up to 2 seconds. So that would be something we would normally have as parameters, but in this case we're just going to have those values in there just so that we can focus on testing this. So we have a public void set life, float time, and this, we kind of have an easy way that we can handle this, because when you do a destroy of a game object, you can give it a time delay. So we'll just do that. What that should mean is these cubes destroy after a time. So if I get here, and we'll keep an eye on the cube registry, and I'm going to spawn a bunch of cubes, and we'll see ones are disappearing, but it's maintaining that list, which means that deregister is happening. Now we want to check and make sure that our register and deregister errors are working. So let's try and register the same thing twice, make sure we see our error message. Again, when you're putting in error cases like of this, test that those errors actually happen. There's nothing worse than, and we get the error, which is good, there's nothing worse than putting in a whole bunch of error checks and they actually don't fire, so the problems get hidden and you think that there's no problem because those error checks aren't happening. So we just want to test both of these and make sure that we get those safety messages so that we know that if something does go wrong, we'll pick it up. And we did, we got the correct message. So that's great, that's what we want to have happen. What this means is we now have this easy registry that if we wanted to, we could loop over and do something. So like our game manager could go, okay, well, if input get key down is key code, and if we go for delete, I could get here and I could go for each var cube in cube registry and the registered cubes, and then I could go destroy cube.gameObject. Now, this will actually be interesting in terms of, depending on the timing, this might fail. Because if this list gets modified while I'm accessing it in a for each, it will actually cause an exception. So we'll spawn a bunch of things and then hit delete and it clears them. So spawn more things, hit delete, they all get cleared. So very, very easy for us to access all of these. So this is the advantage of having that registry approach. So I use that for pretty much any case where I've got something where I'm dynamically spawning stuff. This is a way that makes it really easy to find that code, to track it down, and to be able to easily work with those objects without ever having to do a find object of type or find objects of type, things like of that. You don't need to get components, anything like that, so it's a much quicker, more efficient way of finding them. The key things to be thinking of when you're doing a registry like this is think about how you want to work with that data. If you're churning, adding and removing stuff a lot, I would not use something like a list because that's not great performance for insertion, deletion and searching. If you're adding infrequently, then a list is okay. In particular, if what you're doing a lot is iterating over everything, a list can be great for that. It's generally going to be the best performance there. So do always want to make sure you consider the underlying types that you're using there, because it does matter. It's quite important when you're working with it. Thanks folks, hope you found the video interesting and helpful. If you did, chuck in a like and subscribe, really helps out, it's really appreciated. If you've got any questions, chuck in a comment below. If you're looking for the code for the project, that is available up on GitHub, and you can use that in any of your own projects, commercial or non-commercial ones. And if you're looking for other ways to support the channel, then I do have a Patreon, and there's a link to that in the description as well. But until next time, bye.